Next up, we have Dr., because I'm making her use her title, Anna Bertiger, who's going to talk about my favorite kind of data science, which is practical data science. Anna works in the Microsoft Defender org.
So my name's Anna Bertiger, and I don't know how to tell you how to build a self-driving car. But I do have some thoughts about security. In my experience, security problems often appear quickly. Here's a new vulnerability. We need a detection. And in fact, we'd like it to work yesterday. Often, these problems change over time as the attackers learn about our defenses and learn to evade detection. And they don't usually come with a list of correct answers. And even if someone's willing to tell you the correct answers, it's really just their opinion of the correct answer. And if I surveyed 10 people in this room about the definition of a true positive, and I think I'd get at least 12 answers. So that's going to be strange, because traditional data science wants massive piles of data, assumes the future and the past look pretty the same, and often wants a very long list of correct answers to learn to parrot. So those don't seem like they match very well. So I have found this problem fixed most with compromise. Either do your security with a little bit of math, or do your data science with a solid helping of security. So maybe do some strategic counting. Maybe find some anomalies, but they better be the right anomalies. Or maybe measure some things and cook the measurements together. So strategic counting. Many of you will be mildly triggered by the things on this slide. So last winter, we found a giant vulnerability. Someone found a giant vulnerability in log4j. And a lot of the very early detections were string matching on the string j and di. And then the obfuscations showed up, 35 seconds later. And they look like this. And what we realized was that if you count strategically to sort of say, how much string replacement is going on here, and look for the letters J, N, D, and I, you're going to find a very large percentage of that obfuscation because, oh, string replacement is something you absolutely must do if you want to do some obfuscation here, or at least all of these obfuscation examples. So finding anomalies. Security works on a lot of anomalies, but you need the right anomalous things, because it turns out people are weird. They're strange, they do strange, anomalous, and rare things with computers that no one else in the world has ever done, and that they've never done either, all the time. Like maybe their cat climbed onto the keyboard. But also, only some of these things are a security problem. And if you looked at all the weird stuff, that would be a full-time job for everybody who's worked in security ever for the rest of forever. And it wouldn't be very productive. So you have to look for anomalies that are also likely malicious. And the way to do that is to understand what kind of anomalies are likely to represent security risk and use that to choose what kind of anomalies you look for using statistics. So rare but not malicious, prevalence 1 in the world. Hello world, sincerely Anna, me learning a new language. It doesn't happen very often. I don't produce hashes that are hello world in some new language very often. I'm not one of the people who learns a new language once a week. But perhaps the problem is that if this poor woman has a copy of Service Host no one else has seen in the world, she's probably having a very bad day, unless she's the person who writes Service Host. I caught that person a lot for a while. So the last thing I want to talk about is measuring things and cooking them together. It turns out a good measurement can be really, really, really valuable in this world. So a while ago, someone asked me to find interesting incidents, interesting security incidents. So, and my boss at the time suggested just figure out how to estimate how likely it is to be a true positive and make a list ordered by likelihood of true positives. Because we all like looking at true positives more than we like looking at false positives. And I thought about that for a little while, and I decided, number one, I didn't know how to do that, and it was probably very hard. And number two, and maybe the data is hard to get to. And number two, I thought some more and I decided I'm not even sure it's the right answer. Because if there is a 10% chance it's an APT and a 90% chance it's a false positive. We still probably want to look at that more than we want to look at there is a 99% chance that the AV blocked something it was supposed to block and everything was over at the speed of light. So I took that point of view off to one of my friends and said, okay, let's think this through. So this is sort of a cartoon sketch of how our Defender Experts for Hunting service works. We take this rigorous approach to hunting over our customers' data. We formulate hypotheses to explain data in a potential threat, hunt for and collect observations to support these hypotheses with the help of automated systems, and then calculate a priority that I'm going to talk something about, and then we investigate and analyze and tell our customers that something bad has happened if indeed something bad has happened. So here's a collection of evidence I might be interested in looking at. So you've got some titles over there about malicious URLs and of various flavors, and some credential stealing. And I've labeled things with kill chain stages and with where I got the data. So incidents that are more diverse. So I go off to my friend and I say, I want to find incidents that are likely to be real humans being real troublesome at the top of my list. What makes you think an incident is interesting? You spent a long time as a SOC operator. What do you like? And he said, incidents that are more diverse are more interesting. More kill chain stages are more interesting than fewer kill chain stages, for example, right? More sources are interesting than fewer. So I said, I will figure out how to measure diversity and call you back. And indeed I did. The right answer in this case turns out to be Shannon entropy. Shannon entropy measures how many yes or no questions one expects to ask to identify an element of a set. So if they're all the same, the answer is 0. I don't have to ask you any questions. If I know what possible elements there are in the set, I know what I have. And if they're half red things and half gray things, then I need to ask you one question. I say, is it red? And you say yes or no, and then I know which thing it is. And if there's 16 different things, each appearing once, then I have to ask you 4 questions. Maybe I ask, is it one of peach, pink, maroon, or red? And you say yes or no, and then, or that wasn't enough because I need half of them. Peach, pink, maroon, red, light blue, aquamarine, dark blue, gray, and other aquamarine-ish color. Right, so, and then you say yes or no, and I know which half it's in, and then I chop down some more. And it would take me 4 questions. So if the set has many copy of one things, it's got entropy 0. If it has exactly one copy of each of 16 things, the entropy is log base 2 of 16, which is 4. So because I could not possibly have a collection of slides that don't have some math on them, here's some math. Shannon entropy minus sum of p log p is the formula for calculating this number I was just talking about. So let's calculate an example here. Here's some kill chain stages. Let's calculate the entropy of this set of kill chain stages. So initial access is 4 out of the 5 things here. So probability of drawing initial access is 4 out of 5 if I just pick one of these kill chain stages out of a hat. So its contribution to entropy is minus 4/5 log base 2 of 4/5. And the probability of credential stealing is minus 1/5 log base 2 of 1/5. And if you ask calc to do the arithmetic for you, you get just over 1/2. So I'm measuring diversity for incidents. I measure and calculate the entropy on a bunch of columns. So for example, source and kill chain stage and title, the things I was talking about before in my little toy example. Small worry. How do we compare this number for, say, title, where it might be very large, right? I can have a ton of different evidence, ton of different titles. Could have a set of 1,000 things that are each different. So now log base 2 of 1,000, that's a pretty big number. With kill chain stage, where I can't have more different things than there are kill chain stages. So this is fundamentally, I have to make the units be comparable, right? If I said, this thing's 5 millimeters and this thing's 1 meter, which is longer, you wouldn't say the 5 millimeter thing because 5 is more than 1. So how do we make things comparable? Instead of combining entropy, we combine p-values. So now I've just sent you back to stat 1 if you took it. So p-value is the fraction of numbers for this column that are that value or larger. Now the smallest and largest amounts of entropy for each column are similar, so we can compare those numbers. And using this methodology on other numerical columns and columns like entropy, we can sort of squash all these together. So here's a slide with some toy data on it. So how many numbers on this slide are 1 or larger? All of them, so it gets p-value 1.0. How many numbers on this slide are 3.14 or larger? Gets p-value 0.4 because it and 6.28 are bigger than 3.14, so that's 40% of things. So how do we combine these? Here is the cheap but lacking in statistical technicality thing. It works pretty decently. Sum minus the log of these p-values, then order from largest to smallest. So you can sort of think of this as being like, if I have the probability of heads as a half and the probability of heads as a half, probability of 2 heads as a quarter, I multiply them together, except I use logs because I might have some underflow problems. So that works well. It's lacking in statistical technicality. Here is more statistically technical, but a little harder to wrap your head around. The answer is use Stouffer's method. So pretend these p-values are independent. They're probably not, but it's all right. And combine them using Stouffer's method. Turn each p-value into a z-score. So inverse normal on 1 minus the p-value gets you a z-score. So that's the number of standard deviations away from the mean. Add those z-scores together. You can weight them if you like. So maybe kill chain stage is more important to you than what source it came from. And then divide by the sum of the weights. That will be drawn from a normal, so now I can return you, this is in the top 3% of most interesting ever, instead of just, 47, and then you're like, thanks, that's more than 20. Now you can say, we've got a pile of the 3% most interesting ever. We should start waking somebody up. This day has gone from, usual to terrible. So we actually use this to decide what to investigate while hunting in our Defender Experts hunting service. In exactly the sort of rigorous hunting way that I outlined at the beginning, where we formulate hypotheses and we collect up data and then we try and sort of think about how bad is this collection of data, assuming it's the data we have. So thanks very much. Oh, that's it.